We're nearing the end of our introductory course in finite element analysis. And if there's one thing I think you probably noticed while taking this course, is that we have been performing a lot of integration. In fact, if you just look at this equation we've been examining over the last few weeks, there are 3 different terms that we need to integrate. And in fact, each one of these terms has vectors and matrices in it, and we need to integrate every single member of those vectors and matrices. And I think you'll also agree with me when I say that integration is hard. It's not just hard on us, students and professors. It's also hard for computers. In fact, it's harder for computers. Why? Because when we look at a function, we can easily identify that this function is a polynomial function. And we know the tricks for integrating polynomial functions. Or that this function is a trigonometric function, and I know the trick, or I memorized how to integrate this particular trigonometric function. For computers, it's a lot more difficult to perform integration because computers don't look at functions and immediately recognize if this is a function that they know how to integrate or not. So when we take our finite element analysis methods from paper to programming them into a computer, we need an easier way or a better way for computers to do what's called numerical integration. Another word for numerical integration is quadrature. In this lecture, we're going to examine some ways to perform numerical integration or quadrature. We're first going to look at some basic methods known as the Newton-Cotes methods. We're going to learn how those methods can be improved to something called the Gauss quadrature method, or Gauss quadrature. We're first going to examine and work in 1D, but then we'll extend Gauss quadrature to 2 dimensions. Finally, we'll see how we can apply 2-dimensional Gauss quadrature to the isoperimetric formulations we derived in the last lecture.